Please confirm that you can see the presentation. Hello?
Yes, sir.
Okay.
Yes.
Thank you. Okay, so let us start. We are practically at the end of our course. This is the last week, and this is the first lecture of the last week. So, in the last class, we talked about light being an electromagnetic wave. And in order to do so, I will just briefly revise a few ideas because they are also necessary for what we shall take up later. So these are the four Maxwell equations. Divergence of E is equal to rho by epsilon naught. Divergence of B is equal to 0. Curl of B is equal to minus del L T of B. This is Faraday. And curl of B is equal to mu naught J. That is Ampere's law. Then mu naught plus mu naught into JD, where JD is epsilon naught del L T of E. This is Maxwell's correction to Ampere's law. Now, the source of all electricity as in E and magnetism as in B is the charge. Whether the charge is static or in the case of magnetism, it must be moving. So that is the source of electromagnetism. Now, in free space, where you don't have any charge or current, if you don't have a charge, you will not have a current. So both rho and J will be zero. You will still have the electromagnetic field. So with these four equations, let us look at this. With these four equations, we come to this conclusion that the electric field obeys the wave equation in free space. Epsilon naught mu naught into del 2 del E del T squared is equal to Laplacian of E. And similarly, you get another expression for the magnetic field B. So both E and B obey the same kind of equation. In the last class, we had a long discussion on the wave equation. And then with the help of these two formulae, one involving B and one involving E, we tallied it with the general mathematical form of the wave equation. This is the mathematical form of the wave equation. And with the, on tallying that, what we found that the velocity of the wave matched the speed of light. So this was one great discovery of Maxwell. I will just touch upon two things, and this is the point where we ended in the last class. When we say that light is an electromagnetic wave, this is the formula that we have on our mind. That C as in light, and on the left hand on the left hand side, and epsilon naught as in electro, and mu naught as in magnetic. So light is an electromagnetic wave. If you were to write this thing in a mathematical form, this is the equation that you should use. Okay, I'll just briefly go back to two things to refer to. Let us look at these equations here. First, that if you see, if Maxwell had not introduced this thing, if Maxwell had not introduced this formula, epsilon naught del L T of E, then you would not have got these two equations, this equation as well as this equation. So that was Maxwell's great insight, to bring in this extra correction, and that leads to these four equations. Let us look at these four equations. If you look at it, there is a certain system of unit whereby epsilon naught and mu naught can be chosen to be 1. For the time being, I'm just asking you to think of epsilon naught and mu naught to be equal to 1. Then, I mean, that's a system of unit in which you can do that. Divergence of E is equal to 0, divergence of B is equal to 0. In that case, you will see a certain symmetry about these equations. Curl of E is equal to minus del del T of B, and curl of B will be equal to del del T of E. Right. What do you conclude from the last two equations? That in free space, variation of the magnetic field will give rise to the electric field. This is Faraday. And that thing, variation of the time variation of the electric field, will influence the magnetic field. And so these two equations will be are saying that in free space, the electric field will reinforce the magnetic field and the magnetic field will reinforce the electric field. If you look at these four equations, Second point, third point, I'm sorry, I should have touched on the third point as well. So first point is that these four equations, these equations would not have been possible if Maxwell had not introduced his correction. Second point, there is a certain symmetry about these equations. Time variation of the magnetic field will give rise to an electric field, and that time variation of the same electric field will give rise to a magnetic field, and they'll be locked to each other in a feedback system. That's one thing. And then the other thing is that if you look at these two equations, all of these equations are first order differential equations. First order meaning that they contain first derivatives in the Laplacian operator and time as well. First derivative in the, I'm sorry, first derivative in the vector differential operator and time. Laplacian, I'm sorry, is a second derivative operator. Now, but these two are, this is a first order differential equation, so is this a first order differential equation, but they contain, each of them contains two fields, both E and B. So if you eliminate a field, one of the fields, then you must, the price that you have to pay is a second order differential equation. You see, in this equation, there is no E or there is no B. You just have E. But then you have to pay a price. What is the price? That you have to work with a second order differential equation, both in space as in the Laplacian operator and in time as in the this del 2 del t squared. Just a minute, please. Just a minute. Okay. So there you have that. Now, let us go to the, I mean, this is what we have when we talk about free space, in which there is no charge, and if you don't have charge, you don't have current. But light can also pass through a transparent medium, water, air, glass. So what is going to happen to light? What will happen to light in such a medium? So let us now examine that question as well. Electromagnetic waves in matter. Let's say water or air. And in such a situation, you shall have to use the equation of a material medium. These are the four equations we discussed in the last class, and where you don't have any free charge and you don't have any free current. So like in the former set of equations where you worked only with the E and the B field, here you're now working with the D and the H field. Here you will have these four equations. But then B and H and E and D are also connected. So let us see. B is equal to mu into H, where mu is mu r into mu naught. And D is equal to epsilon into E, where epsilon is epsilon r into epsilon naught. Okay, sorry, just a minute. I'm sorry. I'm sorry about this slight inconvenience. There's something about the audio, I think. Yes. Okay. So if you have D over here, you can substitute that D with epsilon into E, but epsilon is a constant. Epsilon naught, of course, is a universal constant, and epsilon r depends on the material that you're using. But for a particular material, it is a constant quantity. So D can be substituted with this quantity, and since the right-hand side is 0, you can say that divergence of E will be equal to 0, as in this. From this equation, you get this. Similarly, I mean, divergence of B remains 0. Curl of E is equal to minus del del T of B. That also stays the same. And then here you have curl of H. For H, you're writing B by mu. And del del T of D, for D, you're writing epsilon into E. Okay, epsilon is a constant. It comes out of the operator. So this mu is also a constant. So it comes out of the curl operator and goes to the right-hand side. And you can write the fourth equation as curl of B is equal to epsilon into mu into del del T of E. Okay, and what is epsilon and what is mu? Epsilon is equal to epsilon r into epsilon naught, and mu is equal to mu r into mu naught. So basically, you can now decompose this thing like this. So the only difference that you will see now, if you look at these four equations and these four equations that you worked with earlier, these are the four equations that you worked with earlier. The only difference is that in this fourth equation, in the new scenario where you have light propagating through a material medium, but the material medium does not contain free charges and free current. Okay. I mean, they have bound charges, of course, and they have bound current and all those things. Those things are there. It's a glass. Glass is a dielectric material. So you don't have all those, you don't have a dielectric as in an insulator. You don't have free charges. And if you don't have free charges, you can't have a free current either. So the only difference is that the right-hand side of this curl of B equation, this equation picks up an extra factor of epsilon r mu r. So that is what you have for this equation. You don't have to work anything out separately except that this is thing. So wherever you have an epsilon naught, you'll have to put an epsilon in place of that. And wherever you had a mu naught earlier, you will put the mu there. So there you have it. These are the, I mean, you will again get these four equations. I mean, you'll get this thing where V will be equal to 1 by, as you note, epsilon into mu square rooted over. So this and epsilon into mu can now be separated as 1 by epsilon naught mu naught square rooted over into epsilon r mu r square rooted over. And this 1 by epsilon naught mu naught is equal to c, as we discussed earlier. It is the speed of light in free space. Okay, in vacuum. Free space meaning vacuum. So if that is so, then V is equal to C, dimensionally that is how it should be, divided by square root of epsilon r mu r. Note that these two quantities, epsilon, relative permittivity, and relative permeability, epsilon r and mu r, they don't have any dimension. They are just pure dimensionless numbers. And once you have this thing, so what you can do next is N is the refractive index of the medium. Let's say glass or water, whatever you have. That refractive index, I mean, of course, there is Snell's law by which you can define refractive index, but that thing can also be shown to be equal to C by V. What is C? C is the speed of light in vacuum, free space, and V is the speed of light in a medium, as in water, let's say, or glass. So N will be equal to C by V, and that is equal to square root of epsilon r mu r. So again, you can see this equation is also like saying light is an electromagnetic wave. What is N? N is refractive index. It's an optical constant, optical as pertaining to light, optical constant of a particular material. And the right-hand side is an electric constant, epsilon r. It captures the electric properties of that material medium, and mu r is a magnetic property of that particular medium. So mu r is usually, it's very close to 1, unlike epsilon r. Remember, the refractive index can be numbers like 1.33 or 1.5, 1 plus something like that. Diamond has got a very high refractive index. I think it's 2 plus. By the way, diamond is made of carbon, right? And it doesn't contain any free charge. So there you have it. So basically, if this thing is very close to 1, then practically the value of the refractive index is controlled by epsilon r. So to a good approximation, you can write the refractive index as square root of epsilon r, and that is how it is. Now, the permittivity or permeability, both of them are equal to 1 in free space and greater than 1 in a material medium. If that be so, then immediately you will realize that the refractive index is greater than 1. If the refractive index is greater than 1, it is 1.33, 1.5. These are typical values of the refractive index with which you have done, with which you have worked in your school studies in optics. The refractive index is greater than 1. This means that C must be greater than V, or V must be less than C. What is the conclusion to draw from there? That light propagates more slowly, slower in a dielectric medium than in vacuum. Vacuum speed of light is greater than the speed of light in a medium. This is not your ordinary kind of a wave. For instance, if you think about sound wave, sound, of course, needs a medium. If in vacuum, sound does not propagate. But if you have a medium, denser the medium, easier is it for sound to propagate. Sound propagates with a greater speed. So sound propagates in air with a lower speed than sound does in water, and sound propagates much faster in a solid medium. In your school physics questions, you might have encountered this kind of a discussion where you are asked that you can hear the arrival of a railway train uh, from a distance through the metallic rail track than through the air much more quickly. So why so? Because sound finds it is easier for sound to travel through the metallic rail track. Okay, so that is how it is. Anyway, so but light is a very different kind of a wave. It is not your usual kind of a wave. Sound travels faster through a denser medium, but light travels faster at the fastest possible speed uh, in vacuum. In a material medium, light will travel more slowly. So in a glass or in water, the speed of light is not exactly 3 into 10 raised to 8 meter per second. It is less than that. It's somewhere close to 2 into 10 raised to 8 meter per second. I think glass has got a refractive index of 1.5. So V will be equal to C divided by 1.5. So C is 3 into 10 raised to 8 divided by 1.5. So that will be roughly 2 into 10 raised to 8 of that order. Okay. So anyway, so I have this. We shall now. I'll finish this part. I have finished this part of the discussion. What we shall do now is to look at certain properties of plane waves. Let me stop sharing this part of the notes. I hope you are able to follow what I discussed here. We shall discuss something, certain features of light. Just now I told you that sound has got a different sound has got different features compared to light. So we shall now look at certain features of light as an electromagnetic wave. In order to do so, I'll just start a new set of notes, probably the last or the second last set of notes of your course here. Can you please confirm that you can see the presentation? Hello?
Yes.
Yes, sir.
Okay, okay, okay. So basically, what Maxwell achieved was the unification. Well, prior to Maxwell, Ampere showed that magnetism is due to electricity. Then Faraday, prior to Ampere, Oersted had also shown the same thing, but Ampere established it much more systematically that current gives rise to magnetism. Then Faraday showed that changing magnetic flux gives rise to electricity, the reverse traffic. Then Maxwell was able to unify all of them. So electricity and magnetism were all unified nicely. But then Maxwell went a step further and showed that light is a form of an electromagnetic wave. So basically, in one stroke, Maxwell brought optics, which was considered a separate subject of study, as under the purview of electromagnetism. Okay, so let us now see what is it like. We shall discuss a very simple case, plane electromagnetic waves. Let us try to understand what we mean by plane electromagnetic waves. Here is a situation. You have the x-axis, as I have pointed upwards. There you have the y-axis pointing towards you. X swept onto y will give the z direction. So amplitude variation depends only on z. So here's a wave that is an electromagnetic wave that is propagating along the z direction. As of now, we really don't know what is the nature of the wave. We know that light is a wave. Fine, that is all right. But is it a transverse wave? Is it a longitudinal wave? Transverse wave, as in, let's say, water waves propagating on the surface of a quiet lake. That is an example of a transverse wave. Or sound waves propagating through air. That is an example of a longitudinal wave. What is a transverse wave? A transverse wave is one in which the oscillation that goes along with the wave, you can't have a wave without the oscillation, but the direction of the oscillation is perpendicular to the direction of the propagation of the wave. Whereas in the case of a longitudinal wave, as in sound, the direction of the oscillation is in the direction of the propagation of the wave. So transverse, perpendicular to things, whereas in longitudinal, they are in the same direction. So first, we shall try to examine that. But in order to do so, we are keeping our discussion very simple. We are looking at plane electromagnetic waves. What are plane electromagnetic waves? Let's see. So here, just imagine that a whole set of waves all next to each other, just like 3 or 4 trains are traveling parallel next to each other along in the same direction. So there you also have a whole set of waves propagating next to each other in a certain direction. So at any point in Z, if you stand as an observer, you will see all the waves in any direction you look at along the Y direction or along the X direction. What you will notice is that all the waves have the same displacement value. What do I mean by displacement? The wave displacement function. Like I say, Y is equal to A sine kx. Right, A is the amplitude and Y is the displacement. Y is equal to A sine kx, right? So like that, but that's not the equation of a wave, by the way. Wave must have both space and time. Otherwise, there is no such thing as a static wave. A wave must be, I mean, I'm sorry, there has to be there's also something called a standing wave, but that's not exactly what we are referring to. But a standing wave, you still need a time-dependent behavior. So wave equation must obey this kind of, it must have a dependence on time as well as on space. So, but anyway, so what you will find is that all the waves that are propagating parallel to one another, they are having the same displacement function. What do I mean by that? That all of them will reach the crest at the same time. All of them will go to the zero amplitude at the same time. All of them will go to the bottommost trough at the same time. So if you were to draw a surface as a locus connecting all the points with the same phase meaning the value of the wave function, all of them at the crest, highest value, all of them will have the same phase on that plane, or all of them are in the trough, the lowest possible value. So if you draw a surface joining all the waves having the same phase, you will see that the wave has got a plane front. This doesn't always have to be so. For instance, if you have a small bulb, you will realize that the bulb throws out a wave front that is spherical in shape. How will you prove that? Put your hand very close to the bulb, you will see a small shadow. Put your hand very far away from the bulb, or rather, put your hand close to the bulb and cast a shadow very close to the hand. The shadow will be small. If you cast a shadow on the wall opposite to where you put your lamp, then the shadow of your hand or anything will be much larger. It means that the wave front there is not propagating like a plane. For the plane wave front, shadows cast far or close will have the same size, plane wavefront lights like that. So a bulb will throw out spherical wavefronts. A tube light will throw out cylindrical wavefronts. So all sorts of geometrical shapes, geometrical configuration are possible. But here we are talking about plane wavefront. So here that is, sorry, just a minute. So there you have this thing. Now, this is the equation that one obeys when one has to look at, when one is looking at the electromagnetic wave. We are just looking at the electric part of the electromagnetic wave. This is the electric part. Del 2E del T squared, 1 upon V squared. Well, now we know that V is equal to C in vacuum. We are talking in vacuum, so it will be 1 upon C squared, del 2E del T squared is equal to del 2E del Z squared. Why not Laplacian squared? We are just saying that the wave is propagating only in the Z direction. So it is not going in the X or the Y direction. So we are just taking a one-dimensional front, a one-dimensional propagation of the wave. So if it had been, let's say, a spherical front, let's say a point source of light were to have been placed at the origin of coordinates and it is throwing a spherical front, then you would have had to take a three-dimensional dependence. But here we are just taking one-dimensional. We have a tutorial today. In the tutorial today, we will discuss this thing, that the general solution of this equation is just an arbitrary function of z minus velocity into t, either plus or minus. We shall discuss this thing in the tutorial today. We have a tutorial, the last tutorial of the semester. So what we are doing here is that we are writing a general solution like E is equal to E naught, which is the amplitude, into some function of z minus ct. And for plane waves, as we are taking over here, that function is sine kz minus omega t. Sine kz. It can be cos also. Cos and sine, they really don't make much of a difference. Why not? Because cos and sine are simply your convenience of where you are starting from, where you're starting your motion or the initial position. If I give you two infinite wave trains, you will not be able to tell which one is cos and which one is sine. All of cos and sine depends on where you're starting from. So if you start at 0 and thereafter it rises, then it is sine. If you start at maximum and thereafter it falls, it will be cos. So that is what it is. Anyway, but there is a certain advantage of taking a cosine function, but I'll come to that discussion later. Okay. So this function, it depends on z and t. This is a constant amplitude. E naught is constant. You notice that this is just the way you write an oscillatory function or a wave function. Amplitude into the phase part. The phase is either sine or cos. So amplitude into the phase part. The phase part has got this kind of a functional form, kz minus omega t, which is like this, z minus ct. If you take k as a common factor, it will be k into z minus omega by t into omega by k into t. So that is how it is. So this and this are the same thing really, except that you have multiplied. I mean, it's just like saying that k is a part of that f package, kz minus kct, like that, if you like. Okay. Now, E naught is the constant amplitude. The amplitude part is vector, but it's constant. The phase part is scalar, but it is variable. Now let us look at the vector part of the amplitude. E naught is equal to E naught x, x cap plus E naught y, y cap plus E naught z, z cap. Okay, so it is a constant vector, right? It can have all three components. We are not making any restriction. Now let us see, we shall use a Maxwell equation in free space. Divergence of E is equal to 0. If divergence of E is equal to 0, we apply this formula, divergence of E is equal to 0 on this equation. Divergence of E will be del del x of f into E naught x. E naught x, E naught is E naught x cap. So this whole equation, vector E naught into f will be E naught x, f x cap plus E naught y, f y cap plus E naught z, f z cap. When you take the divergence of this thing, it will be divergence of E will be del del x of f E naught x plus del del y of f E naught y plus del del z of f E naught z. That's equal to 0 because the right hand side is 0. Now let us look at each of these derivatives. See, this amplitude is a constant vector, E naught. E naught is a constant vector. If a vector is constant, then it means that its components are also constant. We discussed this thing in one of the tutorials at the very early stages, in the very first tutorial, or probably the second tutorial. I can't remember exactly right now, but I mentioned to you that this is going along, let us say something is happening along the x direction, something along the y direction, and something along the z direction, and all of them add up to a vector. So if the total vector is constant, it means that the components are also constants, because what is happening along x cannot affect anything along y, and neither can y, anything happening along y can affect anything happening along z. So the components are individually constant, which means E naught x is a constant, E naught y is a constant, and E naught z is a constant. But f is not a constant. F depends on z and t. Okay. But we are taking the derivative here with respect to x. So f depends on z and t, not on x. Therefore, as far as the x derivative is concerned, this thing is a constant quantity. Similarly for y. When you consider del del y of f into E naught y, this thing is to be treated as a constant. So derivative of constants of a constant will be 0. This will be 0. This will be 0. You are left with the last part. Del del z of f, E naught z, is equal to 0. So what is this last part going to be like? It will be f del del z of E naught z plus E naught z del f del z is equal to 0. Very good. But E naught z is a constant quantity. Therefore, this thing is 0. If this thing is 0, then of course the first term also is 0. So you're left with the last term. E naught z del f del z is equal to 0. But for the plane wave that we are considering, f is a function of z. And it in our case, it is sine. It can be various other things also, but for this simple plane wave, we are considering f to be a function of z only. So del f del z can't be 0 because when you take the derivative del f del z, you'll get cosine. Sine will go to cosine. So this will not be 0, but this into this is equal to 0. It means that E naught z must be equal to 0 for the electric field. So what does it mean? That the wave is propagating in this direction, but the amplitude of the wave has no component in the z direction. It can have an x component, it can have a y component, because we have not been able to show that E naught x is equal to 0 and E naught y is equal to 0. We have not shown that. It can have those two components, but it doesn't have a z component. No component in the z direction for the oscillation, meaning that the wave is transverse for the E field. For the electric field, this plane wave is transverse. Let us now do the same thing for the magnetic field. For the magnetic field, again, we just do the same thing. See, electromagnetism, what we do now, they are the same thing really, two faces of the same coin. So what we are doing with one face, we can very well do with the other face. So earlier we wrote E is equal to E naught into Fz minus T. And so here we are writing B, vector B is equal to B naught F Z minus Ct. Okay, where Z is, as before, a sine wave. It could be a cosine wave. Once again, I'm stressing that fact. And B naught is a constant amplitude vector, which we are writing as B naught x, x cap plus B naught y, y cap, and B naught z, z cap. Noting that all these three components, values, B naught x, B naught y, and B naught z, they are constant quantities. Next thing, divergence of B is equal to 0. If divergence of B is equal to 0, B naught into F will be B naught x into F here, B naught y into F here, and B naught z into F here. And you have to take divergence of B will give you del del x of this plus del del y of this and del del z of this. B naught x, B naught y, and B naught z are all 0. I'm sorry, are all constants. I'm terribly sorry. And F depends only on z. So for the x derivative over here, this thing is a constant. For the y derivative here, this thing is a constant. So these two derivatives go to 0, vanish. And we are left with the third part. So whatever we did for the electric field, we're just repeating the same algorithm. So what do we do with this last part? F del del z of B naught z plus B naught z del del z of F is equal to 0. Fine. Once we have that, now let us see, B naught z is a constant quantity. If this is a constant quantity, then the del del z of this thing will be 0. So this part also goes away. So basically, you're left with this last term. B naught z del del z of f is equal to 0. But del f del z can't be 0. F is sine kz minus omega t. When you take its derivative with respect to z, you will get cosine. So you are simply left with this into this is equal to 0. This being non-zero, your conclusion is that B naught Z must also be equal to 0. That is to say that the B field also does not contribute an amplitude in the direction of the propagation. There is no component of the B field amplitude in the direction of the propagation. Hence, the B field is also transverse to the direction of the propagation. So if this is the direction in which the wave is propagating, the electric field will be oscillating perpendicular to this direction, so will the B field be. Okay, so we have established two things, that both the electric field and the magnetic field oscillate perpendicular for a traveling electromagnetic wave, for a plane propagating electromagnetic wave propagating along the Z direction. The E field and the B field will not be oscillating along the Z direction. Hence, both these two fields, the waves passing through a wave of the electric field and the wave in the magnetic field, They are transverse waves. Perpendicular transverse wave meaning that the amplitude oscillates perpendicular to the direction of the propagation of the wave. So we have drawn these two conclusions. Now what we shall do, so that's the conclusion, that electromagnetic waves are transverse in nature. So we have taken divergence of E is equal to 0. We have taken divergence of B is equal to 0. Now we shall look at a third condition, Faraday's law. Curl of E is equal to minus del T of B. What we do here now is to write the electric field and the magnetic field like this. You notice that we are no longer writing E naught Z and B naught Z because they have been shown to be 0. So E naught X cap plus E naught Y cap into FZT. B is equal to B naught X cap plus B naught Y cap into FZT, and where FZT is sine KZ minus omega T as before. Okay, now what we shall do, we shall just have to establish an identity. Take the time derivative of B, take the curl of E. Through Faraday's equation, the curl of E will be equal to negative time derivative of B, and then we shall have our result, or we can draw our conclusion from what we will get by establishing this. We'll just have to do left hand side is equal to right hand side. The right hand side is negative time derivative of B. So let us see. This is the B function. B naught x and B naught y are constant quantities. They anyway depend on no variable, not time, not space either. So del T of B, this part will be constant, and this fzt is sine kz minus omega t. So this thing will be del f del t, as has been written over here. And del f del t will be del T of sine kz minus omega t. Sine will go to cos, cosine kz minus omega t, and then minus omega. So this you have got over here. You've got a minus sign over here. So if you take the minus sign to the left, you'll just have plus omega. Why minus sign to the left? Because we have this minus del T of B. We'll come to that later. Now we look at the curl of E. E is this. E naught x x cap, E naught y y cap, fzt. So curl of E will be, write the determinant, x cap, y cap, z cap, del x, del y, del z, E naught x f, E naught f, y f, and 0. E does not contain any z component, so 0 over here. Thereafter, what you do is this. X cap, del y of 0 is 0, minus del z of f, E naught y is anyway a constant, stays out of the derivative, minus y cap, del x of 0 is 0, minus del z of f, you have this thing, and then z cap, del x of E naught y into f. F depends only on z and t, so this will be 0, E naught y being constant, and similarly E naught x is also a constant, and f depending only on z and t, del y of that will also be equal to 0. So there's nothing going along to the contributing to the z direction. So basically you write this thing as minus E naught y del f del z x cap, and then minus into minus plus E naught x del f del z y cap. Okay. What about del f del z? Del f del z is del z of sine kz minus omega t. Okay. And so that will be cos kz minus omega t into k. So that is what you have over here. So curl of E will be minus E naught y into del f del z, which is k cos omega t. So minus k E naught y cos kz minus omega t x cap. And this here is curl of E is the y component is E naught x into del f del z y cap. So E naught x into k cosine kz minus omega t y cap. Okay, and what about the right hand side? Let us look at the right hand side. The right hand side will have minus del T of B. So the minus goes to the right left to this thing. So minus del T of B will have two parts, B naught x x cap cos of this omega into cos of this thing plus B naught y y cap omega into cos of kz minus omega t. So that is what you have. Omega B naught x cos kz minus omega t x cap plus omega B naught y cos kz minus omega t y cap. With the help of Faraday's law, you are now able to say that this thing is equal to this thing, which means that the right hand side will be equal to the right hand side in this top box will be equal to the right hand side of the second box. Now, all we have to do is just match the components. You have got an x component here and a y component here. Similarly, an x component here and a y component here. So let us look at the x component first. If they have to match, then component by component they must match. What have we got over here? Minus k e naught y cos kz minus omega t is equal to omega b naught x cos kz minus omega t. So cos and cos will balance, and you can write minus k e naught y is equal to omega b naught x. Omega b naught x is equal to minus k e naught y. And similarly for the second term, k e naught x, then cos plus omega b naught y into cos. The two cos functions again balance, and then you're left with k e naught x is equal to omega b naught y. So there you have it. So b naught x is equal to minus k by omega e naught y, and b naught y is equal to k by omega e naught x. Okay. Now, we have got these two conditions finally. What do they mean? Let us approach this question from a different direction. First, I'm writing this as this. B naught vector is equal to, I'm just writing this thing, is equal to k by omega into z cap cross E naught. Z cap is the unit vector in the direction of propagation. So this is the direction of propagation. So that is the unit vector. I've just straight away written. You'll ask me why have I written that? I'll tell you why I have written that. Is there any proof? Indeed there is. We shall show the proof. Z cap cross E naught. E naught is the amplitude of the electric field, which is not oscillating along the Z cap direction. Similarly, B naught is the amplitude of the magnetic field. Once again, we have shown that it is not oscillating along the Z direction. I'm just writing this thing. B naught vector is equal to k by omega into Z cap cross E naught. Now let us look at k by omega first. K is equal to 2 pi by lambda. That's the wave number. And omega is the angular frequency, which is 2 pi into nu. You would know these things, I think. So k by omega will be equal to 2 pi by lambda divided by 2 pi nu. The 2 pi and the 2 pi will cancel, and you're left with 1 by lambda nu. And what is lambda nu? Wavelength into frequency is the speed of the wave. In this case, the wave is light. So k by omega is equal to 1 by c. K by omega is 1 by c. Okay. Now, B naught is this thing, E naught is this thing, and Z cap is equal to 1 dot Z cap. Why don't we just take the cross product of these two vectors on the right hand side? So B naught is equal to K by omega into the cross product, which is X cap, Y cap, Z cap. Z cap has got 0 into X cap plus 0 into Y cap plus 1 into Z cap. So 0, 0, 1. And E naught has got E naught X, E naught Y, and 0. There's no Z component to E naught. Then we take the cross, the determinant product, X cap into 0 minus E naught Y minus Y cap into 0 minus E naught X plus Z cap into 0 minus 0. So the Z cap goes away anyway, nothing coming out of there. And so B naught is equal to minus k by omega E naught Y into X cap. And this minus and minus will be plus k by omega into E naught X Y cap. But then B naught is equal to B naught X X cap plus B naught Y Y cap. So when you compare these two things, you can immediately write B naught X is equal to minus k by omega E naught Y, and B naught Y is equal to k by omega E naught X. So mutually perpendicular electric and magnetic vector fields. What do I mean by this? You notice this thing? Z cap cross E naught. If we have just seen for ourselves, follow this point carefully. Follow carefully. Once again, we have just seen for ourselves that E naught and Z cap are mutually perpendicular. That is the property of a transverse wave. We just established that. Transverse wave. E naught doesn't have any component along the z direction. Therefore, whatever is happening is to E naught is happening perpendicular to the z direction. So E naught, vector E naught here is perpendicular to z. But then we also conclude that B naught, I mean, how can we conclude this thing? B naught x is equal to minus k by omega E naught y, and B naught y is equal to k by omega E naught x. We have got this formula, this very formula in this box, we have got through Faraday's equation. You see this thing? We have solved the plane wave function, and we have put the plane wave function in Faraday's equation. And from Faraday's equation, we have got this box, B naught x, B naught y is equal to k by omega minus k by omega and k by omega E naught y, E naught x. We have got this thing from Faraday's equation. And we have got this thing also from this condition. The same formula in the box at the bottom of page 144 is also obtained at the bottom of page 145 from this formula. And what does this formula say? We already know that Z and E naught are perpendicular. Okay. Now we can see that B naught is perpendicular to the cross product of these two things. But this thing must be perpendicular to both Z cap and E naught. Of course, B naught is perpendicular to Z cap. That is the transverse nature of the B field. We have established that also. Electromagnetic B field is also transverse. But now we see something more. The electric field is transverse to the direction of propagation. The magnetic field is also perpendicular to the direction of propagation. And now we see a third conclusion. The magnetic field is also perpendicular to the electric field. If it were not, then this formula would not hold. This means that B naught must be perpendicular both to Z cap as well as E naught, because the vector cross product rule says that the product vector must be perpendicular to the plane containing both the two previous vectors. Z and E are perpendicular to each other, and B naught is perpendicular to both. So all these three vectors, what are the three vectors? Direction of propagation is one vector, the electric field is the second vector, and the magnetic field is the third vector. They are all mutually perpendicular to one another. Mutually perpendicular E and B vector fields, where k by omega is equal to 1 upon c. So we shall now look at certain geometric properties of light. I'll stop the sharing here, and I'll go to a new set of notes. So with this discussion, I'm stopping this sharing. I'll just start basic. I mean, that's roughly the end of it, the end of the course now. Just give me a minute. I'll start the discussion. Sorry. Just a minute, please. It's just starting. Can you please confirm that you can see the presentation? Hello?
Yes.
Yes, sir.
Okay.
Yes, sir.
Thank you. Thank you. So please mute your mics. So we shall just... You remember I gave some supplementary, I mean, I haven't supplied you the notes yet. Please just bear with me. I'm doing some corrections to some errors in the notes. I'll supply it to you as soon as possible. My ambition is to do it within this weekend. Incidentally, just to digress on a point, your exam schedule, tentatively, I think your exam will be held, exams are to start from the 13th. So very likely your exams are going to be held in the last stages. So you still have sufficient time, about 2.5 weeks. So if I can supply you the notes within this weekend, you'll have all of the material. I've already supplied you the tutorial solutions so far, except for 11 and 12, which is to be discussed today. Anyway, so light as a wave. So when we talked about dipole and all that, I supplied you supplementary notes going from A1 to A6. This is another set of supplementary notes, A7, additional notes, not supplementary, A as in additional. So light as a wave, electromagnetic waves. What kind of waves? Transverse waves, as shown by polarization phenomenon. And I'm not touching on polarization here. I mean, we just established mathematically what this E and B fields are like. I'll just touch upon polarization shortly. What do I mean by polarization? So this is just a basic thing about optics, and that's what just you would have studied this at school. So waves of what? Waves in the electromagnetic field that fills all space. Just like you have water, placid water, you throw a stone, and it's a disturbance that propagates in the water. And so it is wave, you have got an electromagnetic field filling all space. A little disturbance in that electromagnetic field will propagate like a light wave. Just like ripples in water propagate as water waves, and so it is that you have the same thing over here. What is the electric field and electromagnetic field? So actually, these are part of a separate course that I used to teach on wave optics. So it's just that. So what is the electromagnetic field? You have got E and the B field. So basically, field concepts are there, and Maxwell's equations, or even Newton's. Let's not worry about Newton's. Incidentally, somebody did try to unify Newton's mechanics with Maxwell's electrodynamics, and the end results were startling. And that somebody was Albert Einstein, but I'm not getting into that. Okay, so I talked about contact force and field force. These are all things we discussed in the early days of the lecture, that field is action at a distance, and you hit a ball with a bat, that is contact force, stuff like that. And in free space, you have these four equations. I discussed all these four equations. Just look at these the third and the fourth equation. The one, electric field is reinforcing the magnetic field, and variation of the time variation of the magnetic field is reinforcing the electric field. It's just like an oscillator equation, and the oscillation property is not very far from light. Okay, let us see. I just briefly going through this thing before I go to the more important page. That is just electromagnetic waves are ripples in the electromagnetic field propagating at the speed of light c with any possible kind of wavelength and frequency. Important point here. You'll say, what do you mean by electromagnetic wave? It's a very, very long, large spectrum. You have microwaves, as you use in your microwave oven at home in the kitchen. Then you have radio waves as in the waves that are received in your mobile phones, that thing. Then you have the visible spectrum. The visible spectrum is the spectrum in which you can see the world in light. Oh, sorry, before the visible spectrum, after the radio waves, you have infrared waves. Infrared meaning lower than infra, below red. Then you have the visible spectrum starting with 700 nanometers, and this goes on up to 400 nanometers. That is violet. So between violet and red, you have the whole visible spectrum. And all of light that you see is simply, white light is a combination of all the colors in the visible spectrum. And you see the whole world within this spectrum. And then beyond the violet wavelength, beyond violet light, you have ultraviolet light. And beyond ultraviolet light, you have got shorter wavelengths like X-rays and gamma rays. So the electromagnetic spectrum is a very wide spectrum, and the electromagnetic spectrum is controlled by the wavelength or the frequency. You prescribe one, the other will be prescribed. Why? Because wavelength into frequency is the constant speed light. Knowing the constant, you just have to know one of the two unknown quantities. You know wavelength, you'll know the frequency, because the right hand lambda into nu is equal to c. So let's say wavelength control. So X-rays and ultraviolet rays, X-rays, gamma rays, these are very short wavelength electromagnetic radiation. Whereas large wavelength electromagnetic radiation are infrared, radio waves, microwaves. Light is somewhere in the middle region, 400 nanometer to 700 nanometer, and you see the world in this light. By the way, not all animals see the world in light. You as human beings have been designed by nature to see the world in this so visible spectrum. There's nothing very special about it. It is just special to you, nobody else. Not to many others. Not, I wouldn't say nobody else, but not to many others. For instance, snakes hunt in the night and they see things. They locate their prey by locating body heat of their prey. So that body heat is detected in the infrared. For instance, in sniper rifles or in night warfare, infrared is used. Infrared glasses, infrared radiation is captured to view the enemy. You'll see these video recording of an eerily green light in which all these things are seen in the infrared region. In eerily green images, I shouldn't use the word light at all. They are not light in our standard sense. And incidentally, it also happened that some creatures don't even need the electromagnetic waves to see. For instance, bats. Bats so-called see with the help of sound, echolocation. So sound is not an electromagnetic wave. Sound is an acoustic wave propagating through the Earth's atmosphere. It's a longitudinal wave as well. So light is nothing very special except to you and many other species like you, but not all species. You see the whole world within this range. So that's why light is important to you. Otherwise, there's the electromagnetic spectrum has got a very long span. So let us now have a geometrical understanding. So this is the important thing I'd like to touch upon, geometrical understanding of light waves. What is it like? This is the discussion I was holding just a while ago. Let us try to see. C is the speed of light. It is propagating along the z direction. Z is the direction of propagation. This is the z direction of propagation. I just discussed all these formulae, right? So I'm not referring to them again. I mean, as you can see, when you say light is an electromagnetic wave, C is the light constant, epsilon naught is the electric constant, mu naught is the magnetic constant. Similarly, N, refractive index, is an optical constant pertaining to light. Epsilon R and mu R are electric and magnetic properties of a material, all those things. So I touched upon these things already. Let's just rather focus our attention on the diagram here. What is this diagram saying? This diagram has it that here is the direction. Z is the direction of propagation. And it is the direction of propagation doesn't have any oscillation of the electric and the magnetic field. Our analysis says, obeying the wave equation, of course, this is the wave equation. Del to E del Z squared is equal to 1 by C squared del to E del T squared, or del to B del Z squared is equal to 1 by C squared del to B del T squared. Okay. There are two properties of waves here. One is the oscillation and the other is the propagation. The propagation is happening along the Z direction. And the oscillation pertaining to the propagation is happening perpendicular to the propagation itself. But we also showed from Faraday's equation, what we have seen is that the electric and the magnetic fields are also perpendicular to each other. So if now you follow extremely carefully, all of you, please be very attentive. If E is oscillating along the x direction, this is the wave that is propagating along the z. This is the oscillation. These vertical strokes, these vertical arrows are indicating the oscillation of the electric field. And B is oscillating perpendicular both to the direction of propagation as well as to the E field. So B is oscillating along the y direction, E is oscillating along the x direction. And because they must be perpendicular to each other, just a while ago we discussed from Faraday's equation. So they are mutually perpendicular. And the wave that is propagating is also perpendicular to both of them. So it is going in the z direction. So x and y are the direction of the oscillation. That part is captured by the second order time derivative. And the propagation is happening along the z direction. And I've also mentioned something, waves, non-localized. Localized meaning something at a point. For instance, a point particle can be said to be localized. It has got a very precise location. But a wave is a non-localized system, meaning you don't have a point-like wave. The waves must be distributed, a wave must be distributed in space, meaning, and in this case, these waves are infinitely long sinusoidal wave trains. So they go all the way to minus infinity, they will all go all the way to plus infinity. I have drawn just two cycles, one cycle here and the second cycle here. Similarly, for the B field, I have drawn two cycles. The B field is oscillating on this YZ plane, and the E field is oscillating on the XZ plane, and they are mutually perpendicular to each other. And also, you notice something, that they are completely in phase. What do I mean by in phase? Meaning, when E field has the amplitude 0, B field has the amplitude 0. When E field has the maximum amplitude, B field has the maximum amplitude. Again, they come down to 0, both of them. Then E field has got the minimum amplitude here. B field has also got the minimum. Well, in the case of the E field, you should use the words up and down, whereas for the B field, you should use the words right and left. Well, right if you are facing the Z direction. I mean, if you are looking outwards along the Z direction, then this is your right and this is your left. So when this goes to maximum up, this goes to maximum right. Both of them again come down to 0. When this goes to maximum down, the E field, the magnetic field goes to the maximum left. And likewise, again, they repeat the same cycle. So they are completely in phase. They are locked with each other, and they are transverse to each other, and they are also perpendicular, both of them perpendicular to the they are transverse waves perpendicular to the direction of propagation, and they are also perpendicular to each other. So this line and this line have a 90-degree angle between the two of them, this arrow and this arrow, likewise for all the other arrows. So here, something else I have to mention. In a wave, the medium does not move. It's only the disturbance that moves. In the last class, I gave you an example of that. I throw a stone on a placid water surface, and the water waves ripple out from the point of impact. But you can test for yourselves that if there is a leaf or a flower floating on the water surface, that will not be carried forward. That will just keep bobbing up and down like this electric field. So it will keep bobbing up and down, but the water wave will propagate forward. What does it mean? That the disturbance, some energy has been injected in the placid water medium. I'm giving you the example of water because it's a very simple thing to recall or realize, or you can even test. So placid water surface is there, you throw a stone. The stone is carrying some kinetic energy. As it impacts the water surface, it transfers a part of the kinetic energy to the water. What will happen to the energy? It will disturb the water, and this disturbance will carry the energy forward. But the medium will not move, it's only the disturbance will move. So the ripple will propagate forward, but the field in this case is oscillating. So just like the height of the water surface is oscillating, is the oscillating quantity, here it is also the electric and the magnetic field are the oscillating quantities. And it's the electromagnetic wave, as in light, that is propagating forward. So the ripple propagates, the field oscillates. Now, okay, then you will ask me, okay, fine, but you just gave the example of water. Water surface is a placid surface, and you throw a stone in it, and it gives rise, the impact of the stone gives rise to the ripples. Okay. In the electromagnetic field, what is giving rise to its own respective ripple? As in, the ripples are the electromagnetic waves, as in light. What is causing ripples here? Here's the answer. Accelerating charged particles. If a charged particle accelerates, again we are going back to charge. Suppose you have got follow carefully, you have got a static charge. The static charge will just give rise to an electric field, no magnetic field business here. But then the static charge is made to move. It will give rise to a magnetic field. So now there is a major difference between my water example and the electric field example. In the case of the water example, the water is completely separate from the stone. The stone might be there or not, or might not be there, but the water will be there. So here, It is not quite like that. Unless you have the charge, there will be no electric field. And unless you have the same charge in motion, there will be no there will be no magnetic field. And then this charge, which is giving rise to both the electric and the magnetic field being in motion, that is, if it is now executing accelerated motion, that is what it is. If it is executing accelerated motion, then it will give rise to ripples in the electromagnetic field. And what is causing the ripples? Here's the answer. We haven't discussed this thing. It's a part of a pretty advanced package, really. That when you have an accelerated charge particle accelerating, it will radiate energy. And what will happen to the energy that is being radiated? It will enter the electromagnetic field and propagate forward as ripples. Just like the energy of the stone on entering the water field or the water medium will cause the transfer of the energy to the water medium, and that energy will propagate as ripples. And so it is that in the electromagnetic field, if a charged particle is accelerating, it will give rise to an acceleration. Okay, let's try to now follow this thing. So you have an electromagnetic field. You can't have an electromagnetic field if you don't have a charge. So let's say some charges somewhere have given rise to an electromagnetic field. And through this field, you're making another charge. Maybe it's the same charge that is the source of the electromagnetic field, maybe not, whatever it is. But if in this electromagnetic field that has been created by charges themselves, you make a charged particle accelerate, then it will transfer energy to the electromagnetic field, because accelerating charged particles radiate energy. And that energy will be carried away as an electromagnetic wave, as light is supposed to be. And the nature of the electromagnetic wave, if you are looking at a plane wave, that's the simplest of all cases. It doesn't always have to be like this. It can be a spherical wavefront. I mean, here I have implied a plane electromagnetic wave. I mean, what do I mean by a plane electromagnetic wave? Let's imagine another wave train going parallel in this direction, another wave train on the other side going in this direction. All the wave trains, like soldiers marching in tandem, all the wave trains will go to their maximum at the same time, minimum at the same time. So basically, if you were to draw a perpendicular plane joining all the phase points, they will the locus this surface will be like a plane. The locus of all points having the same phase is a planar surface. But then suppose you have a bulb, point source of light, then it will be rippling out in spherical front in every direction. Nevertheless, this condition will hold. Whatever be the direction of propagation or anything, E, B, and Z must always be perpendicular to each other. I shouldn't say Z. I would rather generalize it by saying E, B, and the direction of propagation. E, B, and direction of propagation, all these three vectors must be mutually perpendicular to each other. It is easiest to show that thing with the help of plane waves, as has been shown in this diagram. So I hope you have understood this discussion, this whole idea. So basically, optics, as in light, is a subset of electromagnetic waves. And you can't have electromagnetic waves unless you have electricity and magnetism. So they are two faces of the same coin, and the coin is being created by a charge. Charge, static, electricity. Charge in motion, in addition to electricity, magnetism. And charge in accelerated motion will cause ripples in the electromagnetic field so created. Let us just move on. We have discussed the wave equation earlier also, but I'm just adding this thing for a supplementary effect. So we shall be discussing now what is known as the principle of superposition. So here's the wave equation. Del 2 psi del x square is equal to 1 by v square del 2 psi del t square. The psi, I've deliberately written a scalar function, but it can very well be a vector function. So it's a one-dimensional wave. Psi is the displacement function. What do I mean by the displacement function? Remember, this is generally the displacement, the amplitude displacement. The maximum displacement is known as the amplitude. The maximum displacement. Zero displacement here, slightly positive displacement here, maximum displacement here, Again, zero displacement here. So this E here and this B here are the two displacement functions, displacement from the equilibrium value, equilibrium line, right? So displacement function. So here we have just got a scalar displacement function, one dimensional. I'm not talking about light here. I'm just talking about general wave equation. This could very well be applied to the plane propagation of sound waves, because sound is the displacement function of sound, unlike electromagnetic waves, that is light. In the case of light, the displacement functions are the electric and the magnetic fields. In the case of sound, the displacement function is the pressure variation with respect to the uniform pressure or density of the Earth's atmosphere, right? You cause ripples in that Earth's atmosphere, it'll propagate as sound. Right now, you're listening to me because of that. Okay. So this thing can have any kind of solution. It's a linear equation. Linear as in that psi is in the first power, not non-linear. It's not like psi squared or psi raised to 1/3 or sine psi, all those things. No, nothing of the sort. It's just psi. So first power, as in y is equal to mx plus c. Both y and x are in the first power, so that's why. So it can, let's say it has got two solutions, psi1 and psi2. So you can write psi1 here and psi2 here and get these two equations. Del 2 psi1 del x squared is equal to 1 by v squared. Del 2 psi1 del t squared. Del 2 psi2 del x squared is equal to 1 by v squared. Del 2 psi2 del t squared. Then you can add these two equations also. Del 2 psi x squared psi1 plus psi2 is equal to 1 by v squared. Del 2 psi2 del 2 del t squared psi1 plus psi2, which means that if you have got two solutions, psi1 and psi2, then their sum is also a solution. I've written two words over here, which I discussed in the last class, initial and boundary conditions. What do I mean by initial and boundary conditions? That you will need two boundary conditions. A wave is a non-localized object. So it has, let us say, a starting point here. And after one cycle, this is the ending point. So a wave must have an initial starting point and a traveling wave, that is, and a final ending point in this case. A point particle is a point-like localized object, but a wave is a distributed object and it can exist throughout all space. And it has got two initial conditions. Initial meaning as in time. So in one initial, let me give you an idea of an initial condition. I say that at a certain time, this wave function is at its maximum. And at the same time, hereafter, it is now going downwards. So two conditions in time will tell you where the function is in time, what value the function has in time, and what value it is going to have immediately after. So that's what it is. It's a property of differential equations, but it's not my task to discuss all that here. Anyway, the important point that we conclude is that if you have two solutions of the wave equation, then their sum is also a solution. This point is very important in the case of optics because there is something called interference. And that happens because of this principle of superposition. I'll just briefly touch on this discussion. And then in the last class on Friday, we will end our discussion on these few basic ancillary points. So here I've drawn, just give me 2 or 3 minutes. I mean, we still have 2 minutes left to finish this important point. Let us say we have got two wave functions. I have not specified the nature of the wave. Here, this dotted line is the wave function psi1. Here, this continuous thin line is the wave function psi2. Psi1 plus psi2 is another solution. Psi is equal to psi1 psi2. Let us see. The value of psi here is 0. I'm sorry. The value of psi2 here is 0. The value of psi1 here is this. So this plus this will be the sum function because this is 0. So psi will be equal to psi1 plus psi2. Here you notice something. Psi1 is above the line and psi2 is below the line. Let's say that they have the same displacement from this line, one in the plus direction and one in the minus direction. That is being sought to be conveyed over here. When you add these two things, the net effect will be 0. So the function psi is 0 over here. Similarly, if you can come over here, you notice psi2 is above this line, and here psi1 is below this line. Whatever is above is equal to whatever is below. So plus and minus will cancel, and this thick, heavy line psi will again have a zero displacement. So they two can add up to give the same, just the scalar sum. And so the sum, vector sum, in fact, actually, I'm sorry, I should use the word scalar sum, although I've drawn, I mean, plus will cancel minus. That is the whole thing. And so you'll get a zero over here. This gives rise to a very important idea known as interference in optics. You have two wave trains. Let me just touch on this point and we'll end on this discussion. Let us say you have got a wave going like this. Superposed on that wave, you've got another wave going down like this, exactly the opposite. Then this plus arrow will be cancelled by the oscillating minus arrow downwards, and these two waves will just cancel each other. Interference is a phenomenon that arises because of the wave nature of light. If you think that light upon light will give you double the brightness, that is not always the case. Light upon light can give you complete darkness as well. Anyway, so in the next class, we will continue with this discussion. So this thing, I mean, in the class today, we will call your attention to this solution. Psi is equal to f1 x minus vt plus f2 x plus vt. This is the general solution of the wave equation. In the tutorial today, which I shall conduct, we will discuss this thing. Okay, so I shall stop here now. We are already 11:31. In the last class on Friday, we will just conclude this discussion a little. Okay, so I'm stopping the sharing. If you have any questions to ask, you may do so. Otherwise, we may stop the session now. You may please leave. I'll stop the recording anyway. Today we have a tutorial. I'll send you the link of the tutorial very soon.